Hi folks, welcome to another week of off-site learning. I'm going to say it up top this time instead of at the end in case you're clicking out of the video before it's all the way over. Please guys, just make sure you know I'm always here for flex, okay? By phone if you want, by email anytime, or in that Google Doc where you can just type a question, I'll answer it whenever I can, okay? Usually pretty soon. Now, as off-site learning, it can be a little overwhelming at times, so make use of us reaching out to you, right? We want to help you. We're here for you. Okay, so with that out of the way, we are going to keep going through chapter 13. There are new notes in the Google Classroom. They look like this. Okay, so we're starting section 13.3 today, all about reflections. Okay, so you can kind of ignore that note at the beginning because I don't think you'll be writing a diploma. So we'll start on to 13.3, reflection. Okay, so EMR, like every other wave, right? Remember, one of the properties of waves is that they can be reflected. So usually we're focused on the reflection of visible light. That's the type of light we can see, right? We have the most experience with that type of light. However, this reflection applies to all EMR, and this law that we're about to learn applies to all EMR. Of course, all laws that we're going to learn about EMR apply to all EMR, not just light. Okay, so what is that behavior that we're talking about? It leaves at the same angle it entered relative to the normal. So it comes in and it gets reflected and it leaves at the same angle it came in at. Angle relative to what? Not to the surface. That's something that mixes students up sometimes. It's not the angle between the ray and the surface. It's the angle between the rays and the normal line. Okay, so remember, normal means perpendicular. The normal force from physics 20, right, meant it was perpendicular to the surface. So in this case, it's a perpendicular line at the point of incidence. Point of incidence being where the ray hits the mirror. Okay, so in other words, right there, right where it actually hits. So the idea of the law of reflection is really quite simple. The terminology can mix students up, the angle of incidence, the angle of reflection, the incident ray, the reflected ray. But at the end of the day, the law of reflection is actually fairly straightforward. It's just that the angle of reflection is always equal to the angle of incidence. In other words, these two angles always equal. So believe it or not, you have learned the law of reflection before. So you're learning something in physics 30 that you've learned before. Guess when you learned it? Grade 8. Okay, it might have been a while ago, but this is actually junior high stuff, technically. Okay, so the law of reflection, if we have a flat mirror like this, if we have any mirror, as we're going to see, but let's not start off too complicated. If we just have a flat mirror, right, we draw our normal perpendicular to the mirror, right, 90 degrees. Okay, an incident ray is the ray that comes in. It's incident upon the surface, okay? And so the angle between that incident ray and the normal line, not between the ray and the mirror, between the ray and the normal line, is called the angle of incidence. Okay, makes sense? Then it leaves, right? It gets reflected away. That would be called our reflected ray. What do you think that angle is called? The angle of reflection, okay? And so what's the law of reflection? That the angle of incidence always equals the angle of reflection. Okay, this is always, always, always true. Even on uneven surfaces, this is true. So for example, you might be saying, but what about on bumpy things? It does, right? See all those little black normals there, right? You can tell that the law of reflection still holds. It's just that you get scattered rays. And so that's why a nice image doesn't form on things like, well, if you look at your hand, right? Rays are bouncing off of that to your eyes. That's why you can see your hand, but you don't see an image of your face in your hand because they're getting bounced at all kinds of angles and not forming a nice clear image. Okay, so that was actually a slideshow I used when I taught grade 8 in my student teaching. Holds up just fine in physics 30. Okay, so maybe you don't quite believe me, you want to see it for yourself, so I have here just a flat mirror, okay, and a beam of light made by a laser pointer. Okay, now notice if it comes in straight, right? Well, the angle of incidence needs to be equal to the angle of reflection. So if the angle of incidence, the angle between the incident ray and the normal is 0 degrees, well, then the reflected ray is going to be 0 degrees. So it goes in, comes right back the same way, right? If I increase the angle of incidence, there you go. Okay, notice the angle of reflection increases. Okay, so I can draw in a normal line. Okay, and I have to be careful to put my point of incidence on the normal line, otherwise that's not the right normal line. Okay, so see, if the angle between the incident ray, and the normal is 0, well then law of reflection says the angle between the reflected ray and the normal has to be 0. So they go in along the normal, they come out on the normal if I aim it straight on, right? If I increase the angle of incidence, well then you can see the angle of reflection increases as well. Okay, you might be saying to yourself, why make it complicated? Why do we have to use the angle between the normal and the reflected ray and the angle between the normal and the incident ray? Why can't we use just the angles between the rays and the mirror itself? Well, guess what? Not all mirrors are going to be nice and flat like this. So it's true that for a plane mirror, those angles are also equal. That goes completely out the window once we start you doing curved mirrors, which we're going to do. Okay, so like I said, there are going to be a few types of mirrors we're going to see. They're not all going to be flat, regular, plane mirrors. I think of plane meaning boring, boring and plain and flat and regular, right? So a plane mirror looks like this, just a flat old mirror. A concave mirror looks like a cave. We're going to deal with plane mirrors and concave mirrors today. Tomorrow we'll do convex, but if it's a concave mirror, it caves in. Okay, see how that's like a cave, right? Concave mirror. So those are going to reflect light following the law of reflection, something like that. Not going into too much depth now because we'll do it later. Okay, and then convex is the opposite. It's like a bubble mirror. Okay, so a convex mirror looks something like that. So, okay. Now I want to highlight some terminology here. Converging versus diverging. Okay, converging mirrors make the light converge. Converge meaning meet. Notice how rays of light that come in all meet. Diverging mirrors make rays of light spread out, diverge, right? Famous Robert Frost poem, two trails in the path diverged or something like that, means they split apart. So there are three basic qualities to an image that will be formed. Okay, we'll go into what image formation is here in a sec, but that is what size the image is. Okay, that's essentially the magnification. What attitude it has, and where the image is formed, aka type. So you can see the different options here. Okay, I'll go into them in more detail on the next page here. So the attitude or the image orientation, okay, there are two options. It can be erect or it can be inverted. So if it's erect, it has the same orientation as the object, right side up. Okay, so what would that look like? You'd have your object. You're going to see that we use arrows to represent the object and the image. It just kind of simplifies things. What will your image end up looking like? Well, if it's erect, it's upright, it's right side up. So your image will end up looking like that. The other one you can probably guess, if it's inverted, okay, an inverted image has the opposite orientation from the object. So it will look upside down. Okay, so if we start out with an object that looks like that, guess what our image is going to look like? Something like that. Maybe bigger, maybe smaller, but something like that in terms of the attitude. Okay, now there are two types of images. You can have a real image and you can have a virtual image. So virtual image is what you're used to seeing in the mirror, okay? Imagine you're brushing your teeth in the morning. Where do you appear to be? Where does your reflection, the image of you, appear to be? Well, it looks like it's behind the mirror, right? You're not there. It can't be there. Nothing could be there. It's a wall. Well, for most mirrors, right? It's a wall. The thing is not there. There's no way it's actually behind the mirror. And yet it looks like it, right? It looks like it is there. So a virtual image is when the image appears to be in a place where it cannot possibly be. That usually just means behind the mirror, okay? There is actually no light where the image is. When you are brushing your teeth in the morning, there's no person behind some glass who is having light bounced off of them and bounced to your eyes. There's some trickery here. A virtual image is being created. Regular mirrors, like the ones you brush your teeth in every morning, produce virtual images because they look like are they behind or inside the mirror. Okay. Now, a virtual image cannot be projected on a screen. You will never be able to take that, bounce it off, and reproduce the image you saw. So what does a virtual image look like? Well, just to separate it here a bit. Okay, well, a virtual image would look something like you have your object and then the mirror, and the image of your object appears to be over here, where it's not, right? It can't be there because this is a mirror. A real image is when light does make the image, right? So really, light truly is focusing there, okay? It's not just appearing to focus there, and it's producing an image. So you can actually take a real image and project it on a screen. We'll see that when we do lenses. It's true for mirrors too, it's just a little easier to show with lenses. So for example, we'll see a type of real image formation, okay? This might not make too much sense to you now, but just to get an idea, here's my object, and my image is actually going to form on the same side of the mirror. An object could realistically exist there. And so the image does actually exist there because light really is focusing there. So that's what a real image looks like. So what is this idea of an image? How are images even formed? What am I even talking about? Well, you see an image formed when you look in the mirror. Okay, and the reason you see an image formed when you look in the mirror, right? You can actually make out a person in the mirror who looks like you. Okay, the reason you can do that is because light from an object, you, is redirected by reflection to converge, okay, or at least appear to converge to focus somewhere else. In other words, rays of light that are leaving your face, okay, are bouncing off your face, bouncing off the mirror, and then kind of rearranging themselves nicely so that you can reconstruct the image. Okay, so specifically, rays of light leaving the same point converge at another point after reflecting. It needs to be after reflecting, right? So think of it this way. If two rays of light leave your head, right, they both left your head. So if we're going to reproduce an image of your head, we have to see those two rays of light coming from the same place, right? You'll see what I mean when we get into some diagrams here, hopefully. Okay, so on to our first type of mirror, plane mirrors. These are the simplest mirrors, okay? They are just flat, boring, plain, flat mirrors. They are in a plane. So how do we do them? We use the law of reflection. That's really all there is to it, okay? Use the law of reflection, and remember that light will reflect into the observer's eye. Plane mirrors are a little bit different to deal with than we're going to deal with the other ones. That is because they don't have a focal point, which I know doesn't mean anything to you yet, okay? But essentially, all we're doing with plane mirrors is trying to figure out the geometry of it. They're just kind of a nice way to introduce ourselves to the idea of ray diagrams and all that. Okay, so the image will always be the same size as the original object. Another way of thinking about that is that the magnification equals 1x. That will mean more to you later, okay? The image will appear as far behind the mirror as the object is in front of the mirror. So again, think about you brushing your teeth in the morning, right? If you're about 2 feet away from the mirror, how far does your reflection look away? Well, 2 feet behind the mirror, right? They look about as far away from you as you are from them. The wall behind you as you're brushing your teeth looks further away in the mirror because it's further away from the mirror on the real side of things, okay? Another way of saying this, and I'm just writing it down, I know you don't know these variables yet, but we'll get there, okay, is that displacement of the image equals not dO, negative dO, because there's a convention we use here that everything behind the mirror is negative and everything in front of the mirror is positive. Okay, we will get into more definitions of that stuff later when we're dealing with more complex concepts. Okay, so we have our idea here of how images are formed in general and also just looking at for a plane mirror here. Okay, so you have some object, two rays of light are leaving this point. Now, if you were standing in a mirror, you'd be able to see this object. Let's say it's an apple. Okay, so why can you see the apple just normally? Forget the mirror for a sec. Rays of light are bouncing off the apple and hitting your eye, and so you see an apple. Okay, but that would be if you were looking over here at these rays of light, right? But you're not. You're looking at the mirror. And so rays of light from here leave the apple, and then following the law of reflection, so the law of reflection saying angle of incidence equal to the angle of reflection, right? Notice angle incidence equal to the angle of reflection. Same thing here, these two rays that have left the apple, okay? But now they bounce off and they hit your eye. But guess what? Your eye can be tricked, right? Our brains can be kind of fooled because all we're saying is that, hey, I'm seeing light. What does your eye do when light hits it? It says, there's something over there, right? It doesn't know what a mirror is. So your eye says, well, it came from here. It came from here. So I think if I trace these rays back, right? If I trace them rays back, it seems like there's some object over here, right? This reflected ray, if you just for a second pretend these rays aren't there, right? What would you think if you saw those rays? You would say, yep, there's an object over there, right? Our brain's just not realizing that reflected rays are causing us to think there's an object over there, when really it's here. So we get a virtual image because it's behind the mirror, right? There's no actual rays coming to our eyes from here. And in general, we do dotted lines for when we're behind the mirror, for virtual rays. Okay, this is our first kind of ray tracing thing. So I'm going to do it on paper because you'll be doing it on paper. I think if I do it on the board, you're not going to get as much out of it. So I'm just going to switch over to paper and do this so you can follow along. Okay, so ray tracing, what's it all about? It's just about figuring out where will the image form. Now, plane diagrams, like I said, they're a little bit different. We just kind of roll with the law of reflection, okay? Which truthfully we always will be using, but with plane mirrors, it's a little more just, yeah, just do it and see what you get. But with plane mirrors, there's not as much to consider, which ironically actually kind of makes them, I think anyway, a little bit harder. Now, okay, so the question asks, what will be the type, attitude, and magnification of the image? So type, that just means real or virtual. Okay, well, we know plane mirror will make virtual, but let's see why. Okay, so again, to form an image, we need to figure out where rays leaving from the same point end up converging. Okay, or appearing to converge. From her perspective, that means the light needs to get to her eye. Okay, now for plane mirrors only, you usually can't do this, but for plane mirrors, we can kind of cherry pick, right? Because we know that if it's going to leave her head and go to her eye, well, if the angle of incidence is going to be equal to the angle of reflection, for a plane mirror, that just means it's going to hit halfway between, right? So we can kind of cherry pick. I'm going to say, okay, there's her head, there's her eye. So roughly, okay, I'm just going to draw my predicted normal. I have a pretty good feeling it's going to hit there because, well, I kind of know how this goes. Okay, so a ray of light could leave her head. It could bounce off and leave her head, right? And then we would see ourselves if that ray of light ends up bouncing to our eye, okay? Or at least we would see that one ray of light. Now we got to think, what does she think, or what does her brain think it is seeing right now? It thinks it's seeing light that, yes, it is seeing light that came this way, but it thinks the light would have come from, right? Our brains trace it back, and our brain would go ahead and think, it looks like it came from somewhere over here, right? That's what our brain's thinking. So essentially, what is she seeing? She's seeing, looks like a ray that came from over there, if you ignore this one, right? Okay, now for us to start thinking, it seems like there's a head there. Our eyes have to get multiple rays from the same point. In fact, billions of rays from the same point, but we're not going to draw all of them, obviously, right? To agree on where an object is in space, all rays kind of bouncing off of it have to seem to originate from the same place, right? So you are seeing, when I hold this, you are seeing billions of rays hitting this lid here, right? But they are all originating from the same point, and so your brain can reconstruct it and say that, aha, there's a blue lid right here, okay? If the rays that were coming from here were seeming to come from a different, if all rays did not appear to come from here, your brain could not construct an image of a blue marker. So just to say, okay, where will be the image of her head? If we were just looking at this girl and we said, okay, her head is there because all these rays of light that are leaving this point are saying to me, I'm seeing a head there, right? I see a girl's head right there, and so there's a girl's head right there, okay? So how can we start to see an image of a girl's head? Well, if our brain thinks that all the rays of light we're seeing are coming from a girl's head that seems to be over there. So what I'll show you what I mean. So if another ray of light that leaves the girl's head goes like this, okay? Now, notice that ray that I drew came in normal to the mirror, right? It came in perpendicular to the mirror, so the angle of incidence is 0. It's at an angle of 0 to the normal. So the angle of reflection will be 0 to the normal. So in other words, this will come in, and then it will leave right back the way it came, okay? But to an observer that ray of light is going to hit, it's going to appear to have come from behind the mirror this way. Now look at this. Just like we said, okay, anyone getting a ray of light, okay, if we see this girl's head, it's because any ray of light that leaves her head appears to come from that point. Well, look what's happening here. Any ray of light that appears to come from her head, as from these dotted lines, is starting to show us that it's appearing here, right? So realistically, all we need to know is that two rays of light from the same place, okay, after reflecting will appear to come from the same place. So we can actually start to draw our image here, okay? The top of her head will appear there. The rest is actually just going to fall in place. So truthfully, billions and billions of rays are doing this, and we could reconstruct all of them, but it actually only ever takes 2. Usually we'll do a third one to check, okay? But not really so much for plane mirrors. Plane mirrors are treated a little bit different. Okay, now notice what we said about plane mirrors, right? We said the magnification would be 1. In other words, you would not appear any bigger than you thought you were. You would not appear to be any bigger. You would not appear to be magnified, right? Well, look at that. She ended up the same height as she looked before. You know that, brushing your teeth in the mirror. You don't appear bigger or smaller, right? Now, is this image in front of the mirror or behind the mirror? Well, it's behind the mirror, right? She appears to be behind here. So this is a virtual image, okay? Her head was on top, and we got that the rays leaving her head would appear to converge on top again, right? So her head's right side up, so this is erect, okay? And as we already said, she appears to be the same size. Her head is not higher than it used to be. It's not lower than it used to be. So she is the same size. She's not enlarged and she's not diminished. Okay, the next question is actually kind of more the type of question you would get for a plane mirror, because again, these are not ever going to be that interesting. One more thing though, quick, actually, sorry. Notice that she is just as far away. I'm getting about 3 inches and about 3 inches, right? She is just as far away from the mirror as her image appears away from the mirror, okay, by the geometry of our ray. So that's not an accident, right? Ray tracing diagrams are actually something physicists use and have used for centuries to put together how images will form, and they work very well. Okay, now I like this question. Does she need the whole mirror to see her entire body? Okay, so does she need the whole mirror to see her entire body? That is why I kind of cherry picked this ray from her head, because I knew it was going to be useful for us in a sec. So what does that mean, to see your entire body? That means you need to see the top of your head and you need to see the bottom of your feet, right? So that means rays leaving the top of her head need to be able to make it to her eyes. Yeah, great, sure, okay. And now rays leaving her feet need to make it to her eyes. If both of those things happen, then she's good, right? She can see her whole body head to toe. So again, you might kind of get the idea here already just by what I'm about to say, right? If on a plane mirror, if the angle of incidence is going to be equal to the angle of reflection, then a ray leaving her foot is going to kind of need to be halfway between her foot and her eye, right? Because of the geometry at play there. So I'm just going to, again, just kind of cheat about halfway. That'll be where our normal is. And again, it's sort of cheating, but if I got it so that it didn't look like the angle of incidence was equal to the angle of reflection, I would uncheat and I would go back and fix it, right? But you'll see that my cheat works out because if I bring it in, if a ray of light leaves her foot, okay, and now if I say it's going to go to her eye, you'll see I'm not really a cheater because that angle of incidence should look pretty similar to the angle of reflection. Okay. Now, is there any ray of light lower than this to hit her eye? No, right? That's the lowest ray of light she needs to see to be able to see her whole body. So the lowest point on the mirror that any light from her body is going to need to hit her eye is this point. So actually, when you buy a mirror that's as tall as you, half of it is a waste of glass, right? By the way, we can kind of better draw our stick person here by saying, okay, so she would see her foot to be here. Okay, and that's plane mirrors. There is a question in your homework about, there's a question in the practice work that I do really think you should try, okay, or even just try it now as a bit of a homework question. It says, how does this fact change as she moves closer or further from the mirror? Use a ray tracing diagram, see if you can figure that out, okay? I'll give you that as kind of a challenge question. Normally that'd be like a whiteboard. So, does the distance she is away from the mirror change how much of her body she can see? Okay, all right, moving on to concave mirrors. So what's going on with a concave mirror? Okay, well here I have a concave. It could be convex too, but cave, remember, caves in, right? So it's like a cave, it caves in. So it's still just the law of reflection, okay? And so that means that the angle of incidence is equal to the angle of reflection, right? And remember, those angles are to the normal, right? So the difference between a concave and a plane mirror is that the normals are all going to be at a different angle, right? You can actually think of concave and convex mirrors as billions of little plane mirrors. If I would take our old plane mirror, right, and say, okay, what if there was like that, 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 you can kind of start to see that it's making a concave shape, right? So the law of reflection is still obeyed, okay? So here, where the normal would look like that, you can see the ray comes in, the ray comes in at an angle of 0 degrees to the normal, and it bounces back at an angle of 0 degrees to the normal. So this ray is normal, right, at that point there. However, the point up here where it is normal is now, right, up there, the normal is now slightly in like that. So what happens if I bring the ray to be incident up there? Well, the law of reflection is still obeyed, okay? It's just that now the normal is different. So the angles between the normals are going to be slightly different, right? You can kind of see if I keep the parallel, right? Still the law of reflection is being obeyed. It's just that the normal is at a different angle. The normals now go from this angle to horizontal here to this angle down here. And so we get that change here as well if the rays stay parallel. Now, I want you to notice something. All of these rays that I'm sending in parallel, okay, to what's going to be called the principal axis, right? As I send them in parallel, do you notice how there's kind of always a point that it almost seems like the reflected ray is pivoting around? In other words, all of the parallel rays kind of seem to be passing through the same point. Do you see that? Notice how kind of right here, it seems like every ray, no matter where I go through, ends up passing through that point. And I want you to look, if I go closer, okay, now the ray's not showing up that far, but notice how it would still pass through there. What if I go farther? Right? Same thing. Okay, so we would call this the focal point because it's taking rays that are parallel and making them converge. It's focusing them at the point. This is why concave mirrors are called converging mirrors as well. Okay, so just to show you a little bit more simulated what I mean, right? A ray of light comes in parallel. There's the normal line, and angle of reflection equals angle of incidence, right? Okay, what about another ray down here? Comes in parallel, right? There's, right, you can imagine the normal. I didn't draw it in there, but same thing happens, right? There, the normal is slightly more horizontal, and so the angle of reflection is slightly shallower, right? And therefore, it kind of ends up in the same spot, right? You can see this is happening, okay? One that comes straight in still gets reflected straight back, and that is called our focal point. So let's get into some more. Okay, so just some definitions that we need. These are going to take us through not only concave and convex mirrors, but also concave and convex lenses, okay? So where we have a mirror, where rays of light are going to be incident upon it, okay, through the middle of that mirror is called our principal axis. Principal as in important, the main thing, okay? Axis as in, well, axis, right? This is an axis. It's just one line, one dimension, okay? So the principal axis is a line that is perpendicular to the surface of the mirror through the middle of its curve, kind of, okay? Just using color coding on the picture here. You have your principal axis, okay? Your principal axis is this thing here. That's your principal axis. Now, C, the center of curvature. What does that mean? Well, curved mirrors and curved anything, right? You can imagine them as a slice off of a hollow sphere, okay? So you can imagine that this curved mirror here used to be part of a, and this, to be truthful, this one is not drawn very well. It should be drawn a bit less curved, right? But you can imagine that used to be a circle. And what did we do? We cut it here. It was a hollow circle, a hollow sphere, and so now we have this kind of curved mirror, right? Well, notice, if that were a circle, if that were a sphere, at the center would be C, the center of curvature, okay? So the center of curvature, okay, so C, the center of curvature, I will do in green, which just means, hey, what's the distance between this point and C? If this is the middle of the sphere, the midpoint of the sphere, the midpoint of the circle in our 2 dimensions that we're working with here, well then this distance would just be what? It's just going to be the radius of that sphere, right? The radius of that circle in this case. So the radius of curvature is just the distance from the mirror to C, the center of curvature. Okay, as we saw, the F, the focal point, okay, right there, is A, it's half of the radius of curvature. Okay, so this is always true. Okay, by the way, guys, this is all derived in your textbook. It just uses geometry. Okay, in the interest of time and the fact that during this offsite learning period, we're just trying to kind of focus on the main stuff. I'm not going to bother deriving where this all comes from. If you want, your textbook actually does a really good job of deriving all these relationships. So you can go ahead and read through there. For example, why the focal point is where all light rays converge. It explains that. Okay, I mean, it is just angle. It's just the law of reflection at the end of the day, but yeah. So the focal point is always halfway between the center of curvature, C, and the mirror. Okay, so F is always smack dab in the middle of C and the mirror. I'm actually going to go ahead and not call it the mirror. I'm going to call it V. Okay, F, little f, is just the focal length, so you can probably guess. What's the relationship between F and R? Well, if the focus is halfway between the mirror and the center of curvature, and the radius is the full distance between the mirror and the center of curvature, then just like it says here, F is 1/2 of R. Okay. Finally, I alluded to it earlier. V, the vertex. Okay. V, the vertex, that's just where the principal axis meets the mirror. So right there. All right. So you've already kind of seen me. We're going to dive into it now a little bit deeper because honestly, this is where they really are starting to be needed. Okay, is concave mirrors, convex mirrors, and then especially when we do lenses and refraction. So what you need to remember to draw good ray diagrams. Okay, don't even think about trying to do this without a ruler. Okay, you will hate your life. Just do it with a ruler. It makes life easier, makes it look better in the end, will help you out. Okay, all rays of light leave the object, right? All rays of light need to leave the object. They don't leave the image. They form at the image. Okay, all rays of light leave the object. What we're trying to do is form an image from light that has left the object. If it's solid, it's real light. Okay, so if it's solid line, it's real light. Okay, now virtual images or virtual light rays are drawn as dashed lines and they will be behind the mirror, right? That's what makes them virtual. Okay, again, just to simplify, use an arrow pointing up to represent the object and then use arrows to indicate the direction the light is going, and the image will appear where two or more light rays intersect. Realistically, okay, two does the job, one is kind of just a way of checking your work. So I'm going to go to paper again so you can see this. I think it's more useful to see it on paper than for a ghost to just be drawing this stuff, okay? But before we start, these are the rules that are going to carry you through all of the mirror stuff, okay? To be honest, I use two of these mainly, and then I use a third to check. So what I mainly use are rules 1 and 2, okay? So I think of it, I've always just said in my head, PFC, okay? Every time I'm going to do a ray diagram, I say PFC. And what does that mean? It means parallel, focus, or focal point, and center. Okay, so I'm switching over to paper now to show you what I mean. Okay, so this is just kind of a general showing of how to do the rules, right? We could actually get an image forming here if we wanted, but we're just going to say, just to get the idea of ray tracing diagrams, okay? So we have our vertex here where the principal axis meets the mirror, okay? Next, we have the focal point, which is always halfway between the vertex and the center of curvature. So they actually do my rule 2 first, that's okay. Any ray through the focal point will reflect parallel to the principal axis. So any ray that goes through the focal point, and that's what we're going to do. We're going to put one through the focal point. So this is the F part of my PFC. Through the focal point, and then parallel to the principal axis. That's it. That's one of the rays you're going to draw. Rule 2. This is my rule 1. I do PFC. They do FPC. That's okay. Whatever. There's no difference, honestly. So any ray parallel to the principal axis reflects that it passed the focal point. Hey, we knew that already, right? That was what the focal point did. It took rays coming from infinity and reflected them so that they passed through the focal point. So a ray coming parallel to the principal axis will be passed through the focal point. That's kind of the whole point of the focal point. That's rule 2. Okay. Truthfully, guys, want to know something? We can actually already find where our image would be. So I'm just going to do rule 1 on the same diagram here and show you what I mean. So rule 1, again, was anything that goes through the focal point will reflect parallel to the principal axis. So goes through the focal point and then reflects parallel to the principal axis. Look at that. Two rays that left the tip of the arrow now appear to converge here. So guess what is going to look like is there, right? If your eye is over here and these rays of light hit, they're going to go, oh, looks like there's an arrowhead there, right? So that would actually be where our image would be. Now, we should do rule 3 to confirm. What's rule 3? Any ray that passes through the center of curvature reflects back through the center of curvature. That actually makes a lot of sense when you think about what the center of curvature is, right? This to this is just a radius of the circle, right? Any point that passes here is just going to radially go hit the circle. So no matter what, however it hits, it's hitting the circle as if it were some plane mirror, right? It's always coming at this angle, so it's going to be always coming perpendicular. Think about a radius of a circle. A radius of a circle is always perpendicular to the direction of the circle, right? You probably know that from circular motion. The centripetal acceleration is perpendicular to the velocity that is circular. So any ray that passes through the center of curvature reflects back through the center. Honestly, a lot of times when you try to do this rule, you won't actually be able to go hit the mirror, but that's okay because you can imagine if it were a spherical mirror, it should still work, right? So it goes boop and then it comes back. So what I mean when I say this is a confirming rule, this is kind of one for just going ahead and confirming that your work is correct. So let's just see. If we get 2 rays converging, that's great. If we get 3 rays converging, we start to feel pretty good. And look at that, okay? The thing with ray tracing diagrams, guys, they don't need to be perfect. They need to give you a pretty good idea. If I got that a little bit off the center, but it's generally heading to the same place, right? I know I did it right. Where you should start to panic a little bit is if your third one goes nowhere near where your first 2 crossed, okay? That is definitely close enough that I'm saying, yep, feeling okay about that, okay? There's rule 4. Honestly, rule 4, guys, I barely ever use. The reason, notice how those first 3 were pretty brainless, right? We didn't have to think too much about them. We said, okay, parallel and then through the focal, and through the focal and then parallel. You can do that in your sleep, right? It's always the same 2 things. And then the third one through the center and then just back through the center. This fourth one actually kind of requires you to think a little bit, and it's easier to mess up because of that. It also requires a little bit of estimation, which I never like. That is that the light that shines on the vertex will reflect off the mirror at an angle of reflection equal to the angle of incidence. Because remember, if we drew tangents on this curved mirror everywhere, at that point, it would look like a plane mirror, right? So at that point, okay, so if we draw in a mirror array that comes in and hits the vertex, and then it should reflect away at the same angle. But see what I mean? You kind of have to do a bit of estimating here to get, say, okay, that looks about right. So why estimate when the other 3 rules don't really require you to estimate, right? You know what a parallel line looks like. You know where the focal point is. You know all that, okay? So I would say rule 4, only when you really, really, really want to check your work. So again, I can go back to here. Okay, I can try and do that rule just to see. Hopefully it should be pretty close. And if it's not dead on, I'm not going to panic too much. Just trying to make the angle look about the same. And yeah, looks like it's going to confirm my work pretty well. Okay, not bad. So pretty confident that there is an image forming there. Hey, pop quiz, what kind of image is that? Real or virtual? Notice this is our first look at a real image, right? Notice how real rays, not dotted rays, real rays are converging, solid lines are converging to give us an image, right? Another way of thinking about it is that that image is in front of the mirror, right? It's actually, it could exist there. So this is a real image, okay? Is it erect or inverted? Well, our arrow was up and now it looks like it's down, so it's definitely inverted. And it looks to me like it's diminished. It's smaller than it should be. Okay, there's our introduction to ray tracing for concave or converging mirrors. Okay, so we've arrived now kind of at our first set of equations for dealing with mirrors. Honestly, folks, I would love to go through the derivation of these, but honestly, for what you'll get out of it, I'm not sure it's worth the time. Okay, if you would like to see a derivation of them, again, your textbook does an excellent job, I think, of showing where these equations come from, if you're okay with those 3 rules. Okay, so if you read through, if you're not okay with those 3 rules for the rays, you can start there, but page 658 to 662 does an awesome job of showing where these equations come from, okay? However, if you are okay with just accepting them, I think that is where I'm going to kind of go. I'm just going to say, just accept these equations. They work, okay? All right. So these are our equations we're going to use. Just a quick definition of each variable, okay? So we have F being the focal length of the mirror, DO for distance object, so distance between the mirror and the object. Always positive, kind of by definition, okay? Get there in a sec. DI is the distance from the mirror to the image. When it comes to remembering the positives and the negatives, you don't really necessarily have to memorize this stuff. If you can just remember kind of one rule. So you know how in physics 20 or even in science 10, we told you up is positive, down is negative. Well, here's the kind of the rule for mirrors. In front of mirror and behind mirror If that thing is in front of the mirror, it gets to be positive. Guess what? Your object will always be in front of the mirror, right? If it's behind the mirror, it will be negative. That's true for everything, okay? Behind the mirror is considered to be negative. In front of the mirror is considered to be positive. We haven't done convex mirrors. That'll be tomorrow. But their focal point is negative, not for some fancy reason, but because their focal point is actually behind the mirror. Now, they don't truly focus rays there. They appear to. Then looking at this stuff, the magnification, okay? So magnification is pretty simple. It's a ratio of how big the image appears to how big the object really was. So if you appear to be twice as tall, guess what? 2 over 1, the magnification would be 2 times. And it works out, your textbook can show you how the magnification is also equal to the negative of the image distance over the object distance, okay? Again, we have, this is kind of dealing with our side to side, our x-axis almost. This is dealing with our up and down, our y-axis. So again, I'm going to say don't remember any fancy rules. You have your principal axis, okay, your PA, and this goes for concave, convex. Up here above is going to be positive, below is going to be negative. So if your image appears inverted like that, it would have a negative height, right? If it appears right side up like that, it has a positive height. The height of the object is always positive, kind of by definition, right? And we always just draw it that way to make our life easier. You'll never draw your object like this and then go reflect it. You'll always draw it right side up. So magnification, again, if it's greater than 1, if you multiply something by a number bigger than 1, it gets bigger. If you multiply it by a number smaller than 1, it gets smaller. So essentially, all the magnification is saying, how much bigger does this thing look? If it looks half bigger, that means it looks smaller, right? If it looks 1/2 times bigger, it looks smaller. If it looks 1.5 times bigger, then it looks bigger. So it's just the factor by which you multiply it to get its new size. If that factor happens to be smaller than 1, well, then you get a smaller size in the end. Okay, if it flips it, that's a negative magnification. Flips object attitude if it's negative. Okay, so I know I don't like memorizing, okay? However, it wouldn't hurt just as a way to check your work. So plane is easy. It'll always be the same size. It'll always be virtual. And also convex is easy. It will always be reduced. It'll be smaller and it will be virtual. We'll do those next topic. Concave, the one we're doing today, is actually the most difficult. So depending on where the object is, you get a different magnification, okay? A different or attitude, so right side up or upside down. And you can even get a real image and a virtual image. Now, if you were all here, I would show you on a big one, okay? It's really quite cool. You can even actually project an image because you can make a real image. Unfortunately, can't really do that over this video setup that I have. So I will show you kind of a mini version, and that'll have to do. Okay, so if you're following along with that table here, you'll see that for a concave mirror, so we're going to let ourselves be the object, you as in the iPad I'm using to film this part, okay? So you being the iPad, you are going to be the object that's getting reflected. Notice that if it says, if we are between the focal point and the object, we should get an image where you appear to be farther away, okay, but enlarged and virtual. So let's see. Okay, so looking at, okay, so, oh, that's a good angle, okay? So notice how if it's close, you appear enlarged, and so do I, right? You appear enlarged. Okay, that is bigger than the iPad actually is. If I bring my face close, now as I bring it away and bring it away and bring it away, notice what starts to happen, right? So now if you're following along on your sheet, it says, and I want you to think what happens when you're at the focal point. So notice it's starting to get really blurred, okay? When it's at the focal point, remember, all light that passed through the focal point ends up getting reflected parallel off to infinity, right? So imagine if the light source is here at the focal point. Well, then all light passes through the focal point and it ends up doing that. And notice those lines are all parallel. What do we know about parallel lines? They will never intersect. If they never intersect, they can never form an image. So we can find this concave mirror, right? We can find its focal point by finding the point at which no image at all is formed. It's just a total blur, right? So right around there is the focal point. Now we're going to go between the focal point, and the radius of curvature, the center. Okay, so that's this option on the column. So notice how, okay, you go out of focus and then we keep going. And when it starts to come back into focus, notice how now, might just be easier to use me than the iPad, right? Notice how now I'm upside down. So if I come back, right side up, upside down. Okay, so I've got inverted. Between the radius and the focal point, I get inverted. But I am actually also bigger, right? That's bigger than I should be from this far away, okay? Once I go beyond the radius of curvature even, now I start to look smaller than I should, right? You could imagine if you were down on the table looking up at me where my hand is now, I shouldn't look that small. Okay, so to kind of see it in real time with ray tracing, okay, so there's our P and our F, our parallel, and then through the focal point. So they've done the P and the V, they've done the parallel and through the focal point, and then at the vertex and just following a law of reflection. Okay, but we can watch in real time as, right, as this angle gets bigger. So we see that happen, and then look what happens at the focal point. Okay, they are all, and then they switch to the C line. Okay, but you can see now they're parallel, so they won't ever converge, right? And then we start to get a virtual image on the inside, right? And an enlarged virtual image, okay, within the focal point. So enlarged virtual but erect within the focal point. Between the focal point and the center of curvature, we get a real inverted but enlarged image, okay? At the center of curvature, you actually get it so that it's the exact same size, it's just inverted, okay? And then beyond, it's inverted but diminished, but still real, okay? Okay, and the image formation, that is cool, but I unfortunately cannot get that to work with my setup. Okay, so that's all the kind of information. I'm going to stop this video here. I'm going to post another video going through the examples for this same topic. So there'll be another video posted under topic 1 where I just go through some of the examples in the notes if you're more wanting to see that side of things.